You know, we had we learned in 12.3 we learned about our projectile motion, and we actually derived this formula. I also have been telling you don't need to memorize any of these formulas, but you got this V naught cos theta times t, and then this h plus V naught sine theta times t minus 16t squared. That's our position for a launched projectile, launched at a height h with an initial velocity v naught and an initial angle theta. You know, that's its equation. That's its x and y position. Again, I'll give it to you. But I wanted to bring this up, you know, so we derived this. This is the position formula, and I did a few word problems where I needed to sort of isolate x and isolate y, or think about the x position and then think about the y position separately. But I don't know, what in the word problems I did so far, this never came up, but if you ever need its velocity, what is its velocity? Of course, that would be the derivative. I mean, you knew that. But and so I'm going to call this the velocity at any time t. It would be a vector valued function, and I think sometimes students get confused right here. You guys are pretty smart, I suppose you wouldn't, but it's the derivative with respect to t. So the v naught and the theta are constants, therefore the cosine, and so this is a big constant times t, and so we get that constant. And that's a constant, that derivative goes away. That's a constant times t, so we get that constant. And then we get the 32t. Are you guys okay? I mean, that's the derivative. And then its second derivative is acceleration. I guess you know that. But in this problem, it gets kind of boring. Now again, I'm doing this derivative with respect to t. So this is a constant, and its derivative would be 0. And that's 0, and that's negative 32. So, you know, acceleration in this problem isn't too interesting. As a matter of fact, it's just gravity is what it is. It's 32 feet per second down in the y direction. Now notice, there is no acceleration in the x direction. I mean, that's totally, we know that. I mean, all the acceleration is called gravity, and that's in the y direction. There is no acceleration in the x direction, which then brings home this concept, that the velocity in the x direction is a constant. See, if there's no acceleration in the x direction, then you're not changing the velocity in the x direction, so it's not changing, it's constant. And you know, maybe you've seen this in physics class, but what you have at any moment on this curve is you have a y velocity and an x velocity, but oops. When it's on its way up, I think the y velocity might be pointed up. When it reaches its peak, there's your x velocity. There is no y velocity, right? At its peak, the y velocity is 0. On its way down, there's your x velocity. Here's your y velocity. There's your x velocity. Here's your y velocity growing. There's your x velocity. Here's your y velocity growing. So your x velocity, those pictures are all supposed to be remaining constant there. So there's this velocity in the horizontal direction that's just remains constant the entire time. The y velocity is changing due to its acceleration causing it to change. Both the x and y position are changing, but yeah. I don't know, just wanted to think about that a little bit theoretically there. Do you have any ideas? Do you want me to address any problems anywhere? Well, I might take that as a no. Okay. All right. Well, look at this problem. I'm in 12.3, but this is not projectile motion. I just found something else that caught my eye. So I just wanted to briefly talk about that for a second. But in 12.3, there's at the end, there's some other things. Here's something called cycloidal motion. They give me this kind of nasty abstract equation here. R of t is b omega t minus sine omega t. Yeah, b parentheses omega t minus sine omega t. Okay, so the b and the omega are constants of some sort. The t is the variable. And then I have b 1 minus cosine omega t. b parentheses 1 minus cosine omega t. It turns out they're calling this a cycloid. And they refer to this as cycloidal motion. I haven't brought that thing up recently. Here's what a cycloid is. This particular, there's a lot different types of cycloids, but if you took a circle of radius b, that's what we got here, a circle of radius b, and rolled it down the x-axis and watched the path that this point traces out as the circle rolls down the x-axis. The path that this point traces out as it rolls down the x-axis. Well, watch. If you roll it one time, just roll it, half a revolution, then this point will move to this top. Do you agree? After I rolled it half a revolution. And if I roll it another half of a revolution, it'll be back to where it was. And then if I keep rolling it, it does that again. And again. And again. And that's a cycloid. And apparently its position equation at any time is that. I didn't derive that. I didn't want to derive that. I don't know how to derive that. That was derived back in chapter 10, I think. Anyway, it's just a path. It's a path in mathematics. It's a curve in mathematics. It's not a semicircle. It's not a parabola. It's not a sine wave. It's this. It resembles a semicircle, but anyway, it's not. It's the path that a point on a circle traces as it rolls down the road. Anyway, what's this question 43.1? It says, find the velocity and acceleration vectors of a particle that's traveling on a cycloid. Okay. B is the radius of the circle. Omega is the constant angular velocity, the angular velocity. Okay. But what do they want is the velocity and acceleration vectors. Well, I should be able to handle that. How do I do a velocity vector? I take a derivative. With respect to t, I'm going to treat the b like a constant. It is a constant. I'm going to slip past it, and I'm going to come in here, and I'm going to do this derivative with respect to t. Omega is a constant. I know it looks like a w, but it's really a Greek omega. The rednecks call it w, but us sophisticated folk call it omega. The derivative is omega minus cosine omega t. The chain rule spits out an omega right there. Do you agree? When you do that derivative, comma, over here I'm going to hold the b out. And when I take the derivative of the 1, it's gone. When I take the derivative of cosine, it's negative sine, which actually makes it positive sine omega t. It spits out an omega. I'm going to put that out front here. There's an omega. So I just did the derivative. So I have a velocity vector at any point. So now I'm pretending that this is the path of a particle, and at any moment I might have a velocity vector and an acceleration vector. This is not the physics of a of gravity going on here. I mean, this is just a point traveling on a curve. I mean, there's no physical reality of this. So I wonder what the acceleration vector might be. Let me just try to find it here in general below my picture here. Just taking this derivative. Again, the b is a constant. I'm going to slip past the b. But the w goes away. I'm sorry, the omega goes away. I take the derivative of cosine omega t. The derivative of cosine is negative sine. There's already a negative, so it's going to be positive sine omega t. It's going to spit out another omega, though. I think I'll have omega squared sine omega t. Did I just do that right? Yeah. This went to 0. This omega sits here. The derivative of cosine is negative sine, and it spits out another omega. Yeah, this is good. B omega squared sine omega t. What about this guy? Oh, he's easy. The b and the omega just sit there like a constant. The derivative of sine is cosine, spitting out another omega. Okay, b omega squared cosine omega t. Well, that's interesting. Kind of. So I'm just doing it. By the way, I'm doing this kind of abstractly. It's kind of fun to do stuff abstractly. I don't have real numbers. I just got any generic b and any generic omega. So I'm creating these generic formulas in a way for any cycloid. Find the velocity and acceleration vectors of the particle. Use the results to determine the times at which the speed of the particle will be 0 or maximized. Wow. I don't know if I want to do that. I might want to do that. Do you know what speed is? What is speed? When they use the word speed, we're not being loose, we're doing something accurate here. When they use the word speed, do you know what that is?
Is speed the scalar and velocity is the vector?
That's true. So that's exactly true. So can you say that another way, or what does he mean by that? Speed is the scalar, velocity is the vector. That's a nice statement, but what does that mean? So speed is the constant. So speed is the scalar, velocity is the vector. That's what you said. I like that, but
directionless.
Well, right. So it's the magnitude of the velocity. That's what it's right. That's what you meant. Speed's the scalar, velocity is the vector. Okay, but what you meant was, yeah, speed is the magnitude of velocity. So it's when we don't care about the direction and we just want its length, right? We just want its scalar length, right? So that's what speed is. Good. Maybe I'll try that. This might suck though. Here we go. I mean, the magnitude of velocity is the square root of this stuff squared. You know what I'm going to do here? Okay, you know what I'm going to do here? I'm going to factor out this omega. Is that okay with you? Mm-hmm. All right, so then I'm going to square it. So I'm going to have b squared omega squared. And then I'm going to have a 1 minus cosine omega t squared. Did you follow how I did that? I pulled the omega out and made it 1 minus cosine omega t. And then I squared it, right? I squared the whole thing. There it is. Plus that other thing squared, which is a b squared omega squared sine squared. Yeah, there it is. There's the speed in general at any time. I want to clean it up a little. I mean, that's kind of the point, I guess, is to play with these sines and cosines and teach you how to clean it up. Let me just, before I do, I want to show you how easy this is. They didn't ask for this, but can you find the magnitude of this acceleration vector? Let's find the magnitude of acceleration for a second. The magnitude of acceleration, I see it very clearly. I can just tell it to you right now, because not because I'm so brilliant, but I got experience.
It's a Pythagorean identity. When you factor out the bw squared.
Right.
So is it b squared w to the 4?
Well, but then It's in the square root.
So
And then it's,
B
all right, here's what it is. Here's what it is. Here's what it is. It is this dude squared plus this dude squared, right? I mean, that's what it is. So it's b squared omega to the fourth, sine squared omega t, and then this is plus b squared omega to the fourth, cosine squared omega t. Now, what I was trying to do was skip all these steps and get to the answer, but that's okay. So this is, you know how, I mean, this is magnitude, and now if you do factor out the b squared omega to the fourth, you're left with the square root of b squared omega to the fourth times the sine squared plus the cosine squared. What's that?
1.
Thank you. Times 1. You with me, you guys? And then what's the square root of the b squared omega to the fourth?
B omega to the second.
B omega to the second. So the magnitude of the acceleration is b omega squared. And the truth is, I saw that right here. What I saw here was I saw that if you factored out the b omega squared at the beginning, you're left with sine omega t, comma, cos omega t, and I know what that magnitude is.
One.
Thank you. 1. Ain't he? He's a 1. His magnitude. So you can factor out the scalar and then find his magnitude, which is a 1. Sine squared plus cosine squared, 1. Square root of 1. It's a 1. That's a 1. With this factored out, the magnitude is this. I just saw it real clear because I've done millions of these problems. You might not have done enough yet. This one, hang on, this one is a little different, you know? It ain't quite that because it's got this 1 minus cosine. That's messing my, it's not quite as beautiful as that. But we can play the game. You know, I can factor out the b squared omega squared. I can factor it out. It can sit here, but then I could go ahead and pull it out of the square root. If I pull it out of the square root, it's a b omega. Do you agree? Yeah. And then what's left in the square root? This guy, which maybe I'll FOIL him out. He's a 1 minus 2 cos omega t plus a cosine squared omega t. I mean, that's what happens when you FOIL that binomial. And then what's left over here is a sine squared omega t. And then I can group those together and call that 1. And then add it to this 1. So here I am playing around here. This is going to be a 2 minus 2 cos omega t. I can pull out the 2. But if I pull out the 2, it's a square root of 2. But it's a square root of 2 b omega. Then I'm left with 1 minus cosine omega t. How you guys doing? This is my speed. I'm getting it cleaned up as I can. This is it. This is as clean as I can get, by the way. I don't know, I went and messed with that one first. This one was cleaner. This one was less clean. I couldn't quite get this out of here, but that's okay.
Is there a word for the scalar of acceleration?
Yeah, you're right. The magnitude of velocity, we got a word for it called speed. The magnitude of acceleration is just called the magnitude of acceleration. Again, I don't think I have a word for it. Right. By the way, you know, I'm not sure what these acceleration, I know what the velocity vectors look like. I know velocity vectors are tangent to the curve. I know that. I don't know really what the acceleration vectors look like, but they always point to the concave side of the curve. So these are, you know, these acceleration vectors might look like this. You following me? And it's depending on whether I'm speeding up or slowing down or whatever. The one thing I do know about all those acceleration vectors, I don't really know exactly how they're pointing or what they're doing, but I know one thing about all those acceleration vectors. They all have the same length. They got the same magnitude. They have this constant magnitude. Look at them, right? We calculated the magnitude of any dadgum acceleration vector, and that's what it always is. The magnitude of the velocity vector has a variable t in it, so it does fluctuate or change. The length of the velocity does fluctuate or change. It's got a variable in it. the question said, when you figure out this speed, which we've got cleaned up pretty well here, can you tell me when the times, it says determine the times when the speed is 0 or maximized? Well, let's think about this. How's this going to be a 0? I guess this is going to be a 0 if, I mean, that ain't 0, that ain't 0, that ain't 0. The only way this is going to be 0 is if this is 0, which really means the whole square root and everything, but really what's inside the square root has to be a 0, which really means this has to equal 1. Am I right? Or the 1 minus cosine omega t has to be a 0, or in other words, 1 has to equal cosine omega t. When does cosine omega t equal 1? When does cosine equal 1? 0, 2 pi, 4 pi, yeah. So wait a minute, the cosine equals a 1, this quantity equals 0, my speed is 0, is that what I'm saying? My magnitude, my speed is a 0 at these times. I wonder where are those times? I guess those are these times. 0, 2 pi, 4 pi, 6 pi. These must be these funny times. I got no speed for a second there. They're weird little places anyway. There's these sharp points. Huh. Okay. When is this maximized? That's kind of a funny question. This makes you go think about trig. I mean, see, I'm going to think real instinctively here, you guys. Look. You know about cosine and sine. When you input, whatever you input, cosine and sine spit out. I want to say cosine and sine spit out fractions between -1 and 1. Right? That's what they do. They spit out a half, square root of 3 over 2, 0.64. I mean, cosine is, so what am I trying? I'm trying to find out, they asked me, when is this a maximum? And I'm just looking at this and I'm thinking, well, it's going to be a maximum when I can get the most out of this. And I can get the most out of this maybe if it's a 1 and this thing goes to 0. I mean, if I can get him to go to 0, otherwise he won't be a 1. He'll be 1 minus 0.5, or he'll be 1 minus 0.6, or he'll be 1 minus 0.1. You know, cosine will be a decimal somewhere between, oh, wait a minute. What if he's negative? Yeah, if cosine's a -1, that's a maximum. Because if that makes this whole thing, because if cosine's a -1, what's 1 minus a -1? 2. That's the way to make this a maximum. The way to get the most out of this is to make this a -1. So I don't want this to be a 0. I just found my little error. I don't want this to be a 0. I want this to be a -1. Because that'll create the biggest number in this square root I could get. You follow me? So now my question is, when does cosine omega t equal a -1? That's what I've figured out. I want this to be a -1. When does that happen? Well, that's a 1, and 0, and 2 pi, 4 pi. When is it a -1?
Pi?
And probably at pi, 3 pi, 5 pi, right. Which is where?
I guess it's the halfway point.
That's probably here, right? If that was 2 pi and this was 0, then this is probably pi. And that's where I've got the maximum speed. That's where this little particle is traveling the fastest at that time. It must be speeding up toward this place and then slowing down toward this place, speeding up toward this, slowing down toward this. That must be what it's doing. Huh. It reaches its max velocity right there at the peak.
And it's cool because it's the same, if we were talking about velocity, if we wanted the maximum velocity in the x direction, it'd be at the top because most of the speed is going to the right. Right?
Maybe.
Does that make sense?
Maybe.
Because other ones have a y and x component, but at the top it just has an x component.
Right. Right, that's true. And that's when it's a max. It seems like maybe it'd be a max when you got an x and a y component, but not if they're, but you get the most out of that x component up there. You know, I did say something a little wrong here. I said, when does this equal 1? And we said when t is 0, 2 pi, 4. The truth is I made a little mistake there. It equals 1 when the angle is 0 or 2 pi or 4 pi. And the angle is not just t. What is the angle?
Omega t.
Omega t. So I was a little wrong. It would be omega t equals these numbers. And then and we don't know, we're dealing with an abstract omega. So t would be 2 pi over omega, 4 pi over omega. I still think it's those places, but abstractly speaking, that these are the t values where that would happen, I guess, right? Same with this. When I said, when is this negative 1? Those are the angles, but the angle is not just t. The angle is omega t. If we want t, it would be these places, these abstract places. I don't know, that was a decent little problem investigating this cycloid very theoretically in general, but we didn't have any numbers in here, just letters that represent numbers. I kind of like that. You're asked to do that again on 45 through 48. I would suggest you take a look at that one. That's just circular motion. So that's kind of familiar to you. It's circular motion, but they're making you analyze kind of like this in an abstract setting, analyze the velocity, the acceleration, the speed, and so forth for circular motion. So anyway, sometime in your life, look at 45 through 48 in this section 12.3. And it's kind of like this exercise. But maybe we should just quit and take a quiz. What do you think? All right. So Monday we'll come back and maybe I'll review, because you know last Monday I went into 12.4 and then I didn't do too many more examples with that. So anyway, next week, Monday and Wednesday, I hope to do some 12.4, 12.5 work. The truth is, let me just say this. I'm going to give you an in-class quiz right now, but before I do that, let me just announce this. On your way out, I also have a take-home quiz for you. Look at this. It's a piece of paper that looks like this. On one side it says Chapter 12 quiz. Anyway, it doesn't say when it's due, but it's due next Friday on our test. And it's a take-home quiz. And here's what it says. You have to do number 1, but then I'm randomly going to grade the 2 out of the next 5. So number 1's a hell of a problem. Good luck with it. But you got a week to do it. Anyway, and then these other problems, I guess you should do all of them. I randomly grade 2 out of 5 is how I'm going to do it, but I'm definitely grading number 1. The back is called practice. It says practice, so don't get them confused. But the back is not graded. It's just some good problems you might want to practice and ask me about next week. So pick that up on the way out. But right now, maybe I'll just hand you an in-class quiz.